All right, so last class, last topic, we're dealing with potential energy. This is again an extension of what we did last class with work. So work has to do with forces. Forces causing displacements give you work. Work's related to energy through these conservative forces. So if a force does work on an object, it only depends on initial and final position. So doesn't matter how you got there. You're just doing work to move some object from one position to another. And again, it doesn't matter if you took a straight line, doesn't matter if you go up and down. It only matters where you started and where you ended. That's called a conservative force. So it doesn't depend on the path being taken. Some examples of conservative forces are weight or gravity and springs. Example of non-conservative force is friction. So if you have friction between the surface that you're pushing your box on, the longer path you take, the more friction is going to act, the more frictional force is going to take energy out of the system. And so you're going to have to do more work if you push it all around instead of just taking the direct route. So friction is a non-conservative force because the path you take to get from one point to another matters in terms of how much work is being done. For gravity and springs, it's not the case, as we're about to see. So for weight, work required to lift an object, weight W against gravity, is, again, we saw this definition of work is just the force times the displacement. So I'm moving my box from some location down here, has a weight W, weight obviously pushes down, move it along this line to this position up here. So it has some displacement, ds at some location, just drawing it down here in terms of theta between the two forces, or force and displacement. So force W, displacement ds. Now notice I drew it this way, but however, it should kind of be opposite. If I'm pushing this box, moving it against gravity, I'm doing the equal and opposite force. So weight's pulling it down, but I'm pushing it up. So this arrow should actually probably be going upwards instead of downwards. So W ds cosine theta. And then in terms of cosine theta, if I use standard xy coordinates, y being the vertical coordinate, the way gravity acts, ds cosine theta is just dy. So it's only the vertical displacement that matters. So for gravity, u is the integral of w dy, or minus w because w is constant, and then just my displacement, delta y. I put the minus sign back in here because this is the work done by gravity. So this is actually the w going down. So that w goes down, delta y goes up. Opposite direction should be negative sign, as opposed to up here I was talking about the work that you do to move it against gravity. So equal and opposite forces gives me the minus sign. It doesn't depend on the path. Doesn't matter if I went up and down, up and down. It only depends on where I started, where I ended, what's the delta y between those 2 points. So that's the conservative force. Similarly, springs are conservative forces. If you want to stretch or compress a spring, so you want to push on it or pull out on it, stretch it or compress it. Again, the work you need to do on it is F times ds, so F times the displacement, how much you push it in or out. The spring force F is K times S. So total work is K times S times ds. S being, again, your displacement, x0, your equilibrium or unstretched length of the spring. Of course, we're always talking about the work done by the spring. So work done by the spring is the opposite of this. So minus sign comes in, Ks ds. Integrate that, K is a constant. S ds integrated gives me 1/2 S squared. And again, I have some initial point, S1, some final point, S2. So again, only depends on my initial and final positions. Doesn't matter if I go in and out a whole bunch of times. Only depends on where I started, where I ended. So again, conservative force here. Now, potential energy can be made out of any conservative force. So conservative force can give the object the capacity to do work, and that capacity of doing work is called potential energy. So as I said before, a few of the examples we did, if you actually push a body upwards against gravity, that gives it the potential to do work as it falls back down. So if you want to compress a spring by having a big heavy box on top of it, you lift the box up, that gives it potential energy, then you put it on the spring, it uses that potential energy and does work on the spring to compress it. Similarly, if you compress a spring, you can put a ball or something on it and let the spring shoot the ball off, so it does work on the ball. So because these are conservative forces that make up potential energy, it's only the position of the objects that matter. And the position is usually given by some arbitrary fixed origin or data point. So you're basically free to put the origin wherever you want it. Just as soon as you put it there, that's where it is for the entire problem. So a lot of these things that we've seen, the work being done is a change. Gravity is a change in height. Spring is a change in compression of that spring. So because of that, you can arbitrarily set your origin y equals 0 to be anywhere you want. And the actual value of your potential energy is going to depend on that, because if you have y equals 0 way up here, then anything lower than that's going to be negative. But y equals 0 way down the bottom, everything's going to be positive. So the actual value of potential energy is going to depend on what your origin is. But again, it doesn't actually matter, because all we care about is the change. And so because it's only the change matters, doesn't matter where you put that origin. So for example, if I have y equals 0 be this arbitrary line here, the box up here has some positive potential energy because my y value is bigger than 0. I'm assuming W is the actual weight, the magnitude of the weight. If I have my box moved down here below the line, then potential energy is actually negative. But again, I can move this line anywhere I want. So if I move it up here, then both of them are negative. If I move it down here, both of them positive. And so my potential energy is just the weight times whatever the height is, vertical distance from my reference line. Similarly, for my spring potential energy is equal to the work, which is 1/2 ks squared. Again, S equals 0, I can put anywhere I want. Usually you put that where the unstretched spring is. That makes your life easy later. So but you put it anywhere you want, but again, that's the easiest place to put it. Similarly, gravitational potential energy, a lot of times you put it on the ground, so that's a nice, easy reference point. One thing about the springs is because it's ks squared, as I move away from that, S equals 0 equilibrium position, whether compress it or stretch it, it's going to be positive potential energy. That's, of course, if you put it at the equilibrium position. If you don't, then it changes, but that's why it's useful to put it at the equilibrium position. That way your spring potential energy is always positive. Now the potential function is related to potential energy. It's basically the grand total of all your potential energies for a particular system. So if I have several conservative forces, some gravity, some springs, the total potential energy or potential function is the total of all of these. So add up all your potential energies, and that's your potential function. So it could be gravity and the elastic spring potential energy. Could have other things as well. Other conservative forces, you could have more than one spring. So all sorts of stuff, whatever you have going on, to add them all up. This is just for the examples that we did before, where I only have those two things. Now again, if I only have one particular coordinate that these things depend on, so usually this is something like x, the springs we had before on this previous slide, its position can be described by some value x from some reference location. For gravity, it's some position y. Last class, we saw something related to theta. So usually your single coordinate is either x or y or theta. I'm just going to call that some general coordinate q. But again, this is just one of those three things usually. Could be anything, but usually it's one of those three things. So this potential function, all these potential energies only depend on some single coordinate. Again, that's the situation I want because that's the easiest thing I can deal with. So set up some arbitrary origin or datum, and then everything's measured with respect to that, whether it's horizontally, vertically, at an angle, or as an angle. And then in terms of the work being done, that's just the final state minus the initial state, or V at my final position minus V at my initial position, so change in potential energy essentially. So total work done is just the difference between the two potential energies at the two different positions. Or in other words, the change in, or the work is the change in potential energy. So again, that's why I only care about the change in potential energy, because that's what gives me the work. And then again, for statics problems, nothing's really moving. So what I really care about is if something's in equilibrium or not. And if it's in equilibrium, it shouldn't move. If something's not going to move, then the total work has to be 0. Again, I think of this as some virtual displacement. So I have some whatever coordinate I'm dealing with, some delta x, delta y, delta theta, some general delta q, some virtual imaginary movement. Then the total work done, again, that change in potential energy. Principle of virtual work we saw before says that that has to equal 0. So the total change in potential energy has to equal 0. In other words, the derivative of my potential energy with respect to my coordinate q has to equal 0. So this is where it's good to have only one variable for my coordinate. If I have more than one coordinate, I need partial derivatives here, and it gets a lot harder. If I only have one single variable, one single coordinate, get this nice, easy equation. Derivative of potential energy with respect to that coordinate has to be 0. So if that's the case, my system is in equilibrium. That's another alternative way to define equilibrium. All my potential energies, add it all up, take the derivative with respect to some coordinate, and that has to equal 0. Something related to equilibrium is stability. So there's 3 types of stability in terms of equilibrium. So you can have stable equilibrium, you have unstable equilibrium, or neutral equilibrium. So equilibrium means it's not going to move, but then if it does move slightly, what happens? So there's 3 possible cases. Stable equilibrium means if it moves slightly, it comes back to equilibrium. So something like a pendulum hanging down, if I move that slightly to the right, slightly to the left, it's going to want to come back to its equilibrium position. If there's friction in the system, it will eventually settle back down to its equilibrium position. So that's stable equilibrium. Anytime you move it slightly, it comes back. Neutral equilibrium is you move it slightly and basically nothing happens. So something that's nice and balanced, like this double pendulum, one on the top, one on the bottom. If I had it vertically up and down, and I move it slightly to the right, on top, or slightly clockwise, I guess is a better way to describe that, then nothing's really going to happen, because no matter where this this line is, no matter what this orientation is, no matter what the angle is, you're always going to have equal and opposite gravitational forces on each side. So it doesn't really matter what this angle is. It's always in equilibrium, essentially. So neutral equilibrium essentially means it's always in equilibrium. Move it slightly, and it's still in equilibrium. So it's not going to do anything because it's still in equilibrium. Then unstable equilibrium, on the other hand, if you move it slightly, it basically takes off. So this is like an inverted pendulum. So pendulum standing upwards. If you get it exactly vertical, that is equilibrium. It's going to stay there. But any slight nudge left or right, and this thing's going to fall down. So that is unstable equilibrium. So that is potential energy. Again, we'll see some examples of that. So I'm involved in a lot of things, a lot of gravitational forces, a lot of objects, a lot of springs. So we'll see examples of that later today. So I'll see you later for the last official class. Of course, there is still class tomorrow, but that's just you're doing your last quiz. So last actual instruction day. See some examples later.